Okay, so today I'm going to address chapter 22, which is Gauss's law. Gauss's law is the first of Maxwell's laws, which really tells us how electricity and magnetism interact with each other and with charge. Okay. So the rule is that the integral of the electric field dotted into area. That's the flux. We've talked about flux somewhat already. So the integral of E dot dA, but not through just any old surface, but over a closed surface, has got to equal the charge enclosed. Not the total charge in the system, the total amount of charge inside this closed surface divided by epsilon naught. Notice that because it's a closed surface, there's never any doubt about whether you are inside or not. Okay, if I have a surface that is open on one side, and you can go inside there like a cave, then you might ask, at what point am I inside the cave? If I'm right here at the mouth, am I inside? Do I have to be deep inside? Is it out here? That's not an issue if the cave is totally enclosed. You're either in it or you're not. Okay. This is basically simply saying that charges are the sources of electric field. It is a mathematical way of making that statement that I made about electric field lines, where we said the number of field lines is proportional to the charge that they are leaving or that they're coming off of or going into. Okay. So positive charges are the sources where electric field lines start. Negative charges are where they end. Basically, remember we said that the closer together electric field lines are, the stronger the electric field is. So the electric field is proportional to the lines per area. Well, if I dot that into the area, that's the number of lines crossing a surface. Okay. Now, the actual proportionality constant here is not well defined when we're drawing lines. You might decide to draw 3 lines per microcoulomb. I might decide to draw 7 lines per microcoulomb. And our drawings would be equally valid. Mine would just have more lines on it. Drawing the lines is really just a conceptual way of visualizing it. Doing the actual integral of E dot dA is the way to actually find it. And there we have this proportionality constant of epsilon naught. Epsilon naught is known as the permittivity of free space. I don't have any terribly good explanation for what a permittivity is. It's what relates how strong the electric flux is to the charge that's present. Epsilon naught is what you would use in a vacuum. When you are in certain dielectrics, those are insulators, the polarizing of the insulator would weaken the electric field and change the relationship between charge, at least what we call free charge, and the electric field. So permittivities do depend on where you are. This is the permittivity of free space, which today we would call a vacuum. In a lot of ways, this is terminology from the early 1800s. They might still use it in some fields of physics and electrical engineering, but not ones that have been my specialty. Okay. So let's give this a try. We're going to do this one together. The cube in figure 22.6 has sides of length L equals 10 centimeters. The electric field is uniform, has magnitude of E equal to 4 times 10 to the 3 newtons per coulomb, and is parallel to the XY plane at an angle of 53.1 degrees, measured from the x-axis toward the y-axis. What is the electric flux through each of the 6 cube faces? 1, 2, 3, 4, 5, and 6. What is the total electric flux through all the faces of the cube? So I'm going to figure it out for the top, front, and back. And I will leave it for you to figure out the value for the flux through the left and right sides and the bottom. Okay. Now, in doing this, it's useful to look and see they said the electric field was entirely in the XY plane. And they said that this angle from X towards Y is 53.1 degrees. Okay. So that means there's the E vector. Here's the x-axis, here's the y-axis. This angle is 53.1 degrees. So I know that the electric field is going to be EX in the x direction, so I hat, plus EY in the j direction, the y direction, plus EZ in the z direction, k hat. But because they said the electric field was parallel to the xy plane, that means EZ is 0. Okay. And EX is going to be E times the cosine of 53.1 degrees. Now you can put this in your calculator to find it out. I happen to know that 53.1 degrees is the big angle in a 3, 4, 5 triangle, which means this cosine is 3 over 5, or 0.6. All right, what does that do for us? Okay, well, maybe I'll keep it green for a moment later. So EX is equal to 4,000 newtons per coulomb times 3/5, and that is 2,400 newtons per coulomb. Okay. Now let's figure out the various area vectors. Each area is a square of length 10 centimeters, or side 10 centimeters, times 10 centimeters. That means each one is 100 centimeters squared. Of course, that is also 0.1 meters squared, which is 1/100th of a meter squared. And as far as the direction goes, S2 is on the top. It points straight up along the z direction, so that is in the k hat direction. S5 on the front is going to point out. For Gauss's law, the area vectors always point out. That is the positive direction for a closed surface. It's not so easy to define a positive direction for an open surface, but for a closed one, it's outward. So this is in the x hat or I hat direction, and S6 is in the negative I hat direction. So coming here, the flux through side 2, that's the top. That is going to be EX. Oh, sorry, the flux through a side we know is the integral of E dot dA. Over the entire surface, the direction of the area vector and the direction of the electric field is constant. So E is constant, I can pop it right out. I can integrate dA to get A. So over a single surface, this is just E dotted into A. So over 2, I've got EX, A2X, but A2X is 0. We also have EY, A2Y, but A2Y is 0. And then we have EZ, A2Z. Now A2Z is not 0, but EZ is, which means the flux over that surface is 0. The electric field never crosses through the top surface. Okay, now let's do side 5. That should be EX times A5X plus EY, A5Y, plus EZ, A5Z. Now it happens that EZ is 0, as is A5Z. EY isn't 0. I haven't found it for you yet. You're going to have to do that. But, so EY isn't 0, but A5Y is. A5 is entirely in the x direction. So I just have EX times A5X. That is 2,400 newtons per coulomb times 0.01 meters squared. And that just becomes 24 newtons meters squared per coulomb. Okay. Now, 5 and 6 have the exact same magnitude. They're the same size square, but they point in opposite directions. So that means A6 is just negative area 5. And the flux through side 6 is equal to E dotted into A6, but that's just negative E dotted into A5, which is negative flux through 5, or negative 24 newtons meters squared per coulomb. Okay, and what does that all come down to? Or what is it total if I add those three? Well, if I add the flux through side 2, plus the flux through side 5, plus the flux through side 6, this is 0 plus 24 newtons meters squared per coulomb minus 24 newtons meters squared per coulomb. And that totals to 0. So those three sides, at least, the total adds up to 0. You will have to figure out whether what the total for sides 1, 3, and 4 are, whether they also add up to 0 or something else. If the whole thing is 0, that means there are no charges enclosed in that cube. And we know that I can set up that we can set up a nice constant electric field by simply having two oppositely charged plates close together. Okay, a positive and a negative. So if that cube were inside there, the charges could all be on the outside, and we would have that constant electric field piercing through the cube, just like we saw. All right, so I will let you try the rest of this problem.